Good morning, champs. Same gas, same starting point, same final volume. But depending on the process, the required compression work changes. Why? Because on a pressure volume diagram, work is area. Let's first recap the three process paths. First, isothermal compression. Isothermal means constant temperature. The process follows P times V equals constant. During compression, heat leaves the gas, so the temperature stays constant. Second, polytropic compression. A polytropic process follows P times V to the power N equals constant. This describes real compression between idealized cases. Third, isentropic compression. An isentropic process follows P times V to the power kappa equals constant. Isentropic means reversible and adiabatic. So there is no heat transfer and no irreversibility. Kappa is the ratio of Cp to Cv. For this example, we use Cp equals 1.30 and Cv equals 1.00. So kappa equals 1.30 divided by 1.00, which is 1.3. Now draw all three curves on the same pressure volume diagram. The isothermal curve is the flattest, the polytropic curve is in the middle. The isentropic curve is the steepest. The steeper the curve, the larger the pressure during compression. And larger pressure means larger work. Now let's connect this to the work equation. Boundary work is the integral of pressure with respect to volume. For compression, the volume decreases. So when we talk about positive work input, we use minus the integral from initial volume to final volume. Now let's calculate. Air is compressed from 1 bar and 0.10 cubic meters to a final volume of 0.03 cubic meters. We compare three cases: isothermal, polytropic with N equals 1.15, and isentropic with kappa equals 1.3. First, the isothermal case. For isothermal compression, P times V is constant, so pressure equals P1 times V1 divided by V. We insert this into the work integral. The work input becomes minus the integral of P1 V1 over V dV. Since P1 and V1 are constants, we take them outside the integral. The integral of 1 over V is the natural logarithm of V. After applying the limits, we get work input equals P1 V1 times the logarithm of V1 over V2. Now insert the values. 1 bar times 0.1 cubic meters times the logarithm of 0.1 over 0.03. This gives 0.1204 bar cubic meters. Since 1 bar cubic meter equals 100 kilojoules, the work input is about 12 kilojoules. The final pressure is P1 times V1 over V2, so 1 times 0.1 over 0.03 gives about 3.33 bar. Now the polytropic case. For a polytropic process, P times V to the power N equals constant. So pressure can be written as a constant times V to the power minus N. From state 1, the constant is P1 times V1 to the power N. We insert this expression into the work integral. Then we integrate V to the power minus N. The result simplifies to the common polytropic work formula. Work input equals P2 V2 minus P1 V1 divided by N minus 1. Now use N equals 1.15. First calculate final pressure. P2 equals P1 times V1 over V2 raised to the power N. So P2 equals 1 times 0.1 over 0.03 raised to the power 1.15. This gives about 3.99 bar. Now calculate work. Work input equals 3.99 times 0.03 minus 1 times 0.1 divided by 1.15 minus 1. This gives about 0.131 bar cubic meters converted to kilojoules. This is about 13.1 kilojoules. Now the isentropic case. For isentropic compression, P times V to the power kappa equals constant. Here kappa equals 1.3. Calculate final pressure. P2 equals 1 times 0.1 over 0.03 raised to the power 1.3. This gives about 4.78 bar. The work equation is the same form as before, but now n is replaced by kappa. So work input equals P2 V2 minus P1 V1 divided by kappa minus 1. Insert the values. 4.78 times 0.03 minus 1 times 0.1 divided by 1.3 minus 1. This gives about 0.145 bar cubic meters. Converted to kilojoules, this is about 14.5 kilojoules. Now compare the results. Isothermal compression needs about 12 kilojoules. Polytropic compression needs about 13.1 kilojoules. Isentropic compression needs about 14.5 kilojoules. So the order is isothermal is smallest, polytropic is in between, and isentropic is largest. Same initial state, same final volume, but different paths. And because work is the area under the pressure volume curve, different paths require different work. The pressure volume diagram is not just a drawing. The area under the curve is the work.